Okay. Hello, everyone. My name is Wang Zhenqiang from Harbin Engineering University. It's a great honor for me to present some recent work. My topic focused on the effect of moly on carbide precipitation in austenite of titanium microalloyed low carbon steel. In 2004, a high-strength steel nanohydrate was developed by JFE Cooperation Japan. This steel has been massively produced in million tons 1 year. They are used in the production of suspension of vehicle due to its good mechanical properties, including high strength, high ductility, especially excellent hole expansion ratio, up to 120%. Its microstructure is pure ferrite, and it is strengthened by the interface precipitation of titanium moly carbide. The contribution of precipitation to the yield strength reaches 3 million Pascal, and the complex titanium moly carbide is a kind of corrosion resistance carbide. But one thing we neglect usually is the grain refinement of this steel. The grain size is about 3 micrometer, and the contribution to the yield strength from grain refinement is about 280 millipascal. This is related to the austenite conditioning before cooling, and it is affected by the strain-induced precipitation in gamma. A question is, what's the effect of moly on the precipitation in gamma? So we design and melt two alloys. One is titanium moly steel, and the other is titanium steel, to study the effect of addition of 0.2% moly on carbide precipitation. And this is a double heat compression test. We have obtained the softening ratios versus time curves of gamma after gamma deformation. This is associated with the gamma recreditation, precipitation, and their interactions. OM is used to see austenite morphology. TM is used to analyze precipitate morphology and composition. Hot rolling and physical chemical phase analysis are used for quantifying the precipitate. XRD is used to measure the lattice parameter precipitate. Thermocalc is used for thermodynamic calculation. And when the worry plus DLP-NBB theory is used to calculate the interfacial energy of MC carbide gamma system. And we plot the softening ratio curves. We can see at higher temperatures, for example, 1000 degrees centigrade, the two curves exhibit S-shapes for the two alloys, implying that the gamma recreditation persists without pinning from precipitation. At 950 degrees or below, clear plateaus appeared, indicating that the crystallization process are delayed due to the precipitation. We use the RME relation to determine the start time of the precipitation. The start time of which the relation deviates from the linear relation is defined one side of precipitation. So we get the precipitation start time curves. We can see that the decision of 0.2% merely moves the PSTT curve to the left, meaning that merely can accelerate the carbide precipitation. We conducted hot rolling plus physical chemical phase analysis for quantifying the precipitation, and the precipitates are extracted from the samples. Elements were measured. We can see that the precipitation fraction increased with Morley addition. We employ small angle X-ray scattering method to measure particle size of precipitates. We can see Morley addition refine the carbide precipitates. We also use the carbon replica to observe the precipitates. Compared titanium steel, titanium Morley steel has a more refined precipitates for long time holding, half an hour. It revealed that Morley decelerates the course of precipitates. And we also observed the pure austenite grains before deformation. The gamma grains are equals. After deformation, the holding for 10 minutes, some fine gamma recrest grains can be seen for titanium steel, but not for titanium Morley steel. This indicates that austenite grains recreation is delayed by Morley addition. We employed EMEDS to characterize the precipitates. We can see that B1 structure for the two carbides Morley incorporate into the titanium carbide lattice substitution of titanium, which conflict with the general understanding that Morley carbide is B1 structure and hardly precipitates. And the precipitates exhibit cell-like distribution on carbon replica, indicating that the nuclear on dislocation or dislocation substructures or the microband formed by deformation. Interestingly, a core shell structure with Morley enriched shell is observed for titanium carbide precipitates. And the thickness of the core shell structure is about 2 nanometers. So we know that the carbides exhibit tetracardec shape in austenite. So we tailed the electron beam TM 011 axis to counterline the projection of the carbide on the plane 100 or 111. So we used the nano beam EDS with a small size of 1.5 nanometer to measure the composition of the shell. The precision of the shell is indeed reached with Morley. It is about 2 nanometers thickness and contains almost the same Morley and titanium. We further analyze the areas composition. We can see the sub-lattice fraction of Morley decrease with particle size. We use Taylor expansion to determine the area value. The sub-lattice fraction is titanium 91 Morley 8 iron 1 carbide. That in shell, a titanium 47, Morley is 47, iron 6, and the average thickness of shell is 1.26 nanometers. So let me briefly make a summary. First, Morley accelerates MC precipitation austenite. Second, Morley slow down the crossing of MC process. Third, Morley incorporates into titanium carbide lattice. Fourth, the fraction of Morley decreases at the particles up and the core shell structures. Fourth, so expressing what drives the occurrence of this phenomenon. Deep free energy, differential energy. Perenina calculates the solid solution solubility, B1 structure and Morley carbide, and external Morley 2 carbide in austenite. We can see that the solid solution product of both Morley carbide are 2 to 6 orders of magnitude higher than titanium, higher than that of titanium carbide in austenite. So pure Morley carbide can hardly precipitate in austenite. We also calculated the deep free energy and found that deep free energy is relatively larger for Morley carbide than titanium carbide. These results are consistent with the general understanding. Somakak also confirmed the result. Also confirmed Morley hardly incorporates MC carbide in austenite, but in ferrite, Morley can incorporate to the lattice. So we have to check the barrier of the precipitation interfacial energy. We know that so we calculate the interfacial energy, including structure part from the misfit and the chemical part. It's known that MC carbide obey cube-on-cube orientation relationship. We calculate the misfit often. The structure parts are very similar for titanium carbide, titanium Morley carbide, because they have very close crystal parameters. They are determined by XRD. Then we can employ DLP, MNBB, to calculate the chemical mass. This is a figure for the 3 didactics. We can see that in the incorporation of Morley into MC carbide precipitation lead to the decrease in the interfacial energy of MC gamma interfacial. These favorite clearance of titanium carbide, the formation of core shell structure, and also delay the causing of the complex carbides. So we make a conclusion. First, 0.2 Morley addition to the titanium Morley alloys still promotes the declaration of MC precipitation and retard the crossing. And the titanium Morley carbide particle is a core shell structure observed to form austenite. The core is identified as titanium enriched. The shell is an average thickness of 1.26 meters. Identified titanium Morley enriched. The crossing kinetics was found to be decelerated by the core shell structure. Third, thermodynamic calculations of that is replacement of titanium Morley in titanium lattice and favorable for MC declaration from the deep free energy side. However, it decreases the interfacial chemical energy system of this system. The second decrease for pronouncement the MC precipitation are relatively small, thus accelerating MC declaration. Okay, thank you very much. That's all.